Good afternoon. This is Jerry Tuttle, and my topic is what is data science? Just as background, I'm a Florida resident. I'm a retired actuary. I teach math online for Rocky Mountain College of Art and Design, and I'm a fledgling data scientist / data analyst. I'm going for a master's in data analysis at Southern New Hampshire University. There's a lot to data science. It's quickly making its way down through the graduate school curriculum, into the undergraduate, into the two-year college, and I think it'll be in the high school curriculum before you know it. So let's learn a little data science. So what is data science? Data science is the intersection among math and statistics, computer science, and domain knowledge. Domain knowledge means some understanding of the application of the data. And the purpose is to extract meaningful insights from data, translating into tangible business value. So this is a very applied subject. What can we learn from the data of some value that we can make some money from? So here are some basic data science problems, the general category they belong to, and the techniques. We can determine relationship between the outcome and the input. That's regression. Regression often uses linear regression. Linear regression, the output variable is a continuous variable. In logistic regression, the output variable is categorical and is usually a yes, no, or a small number of terms. We can group items by similarity, that's called clustering, and for two of the algorithms are k nearest neighbor and k mean. We can find the relationship between items, that's called association rules, and the technique is a priori. We can assign known labels to objects, that's called classification, and we use decision trees and random forests. And we can analyze text data, and that's called text analysis. Before getting into the algorithms, this is something I've discovered from data analysis that's a big difference from it and statistics, in that in data analysis, we generally don't use 100% of the data to create the model. We generally randomly assign, say, 80% of the data to train the model, and here I'm randomly assigned the blue dots, the blue squares, as my training data. I've trained the model with the blue dots, and now once I have the model, which here is a straight line, I'm going to test the straight line against the remaining 20% of the data which the model hasn't seen. And then I'm going to measure performance against the testing data. So here I'm measuring the root mean square error of actual versus predicted on the red data. And that's something we don't generally do in statistics. Generally in data analysis, we have some actual data. We're trying to make predictions on it, and assuming it's a yes-no type of predictions, we can take our data after we've run the model, and we can allocate it into one of these four categories, depending on yes or no on the actual, yes or no on the predicted. A false positive is what we call type 1. That's when the doctor tells the male patient that he's pregnant. A false negative is the type 2. That's when the doctor tells the obviously pregnant woman that she's not pregnant. And with these four categories, there are a number of measures we can calculate. Accuracy is true negative plus true positive divided by the total number of items. We can calculate the true positive rate or the positive predictive value, and several other measures. Generally, we start a data analysis problem by exploring the data. So here is a small piece of a data set of 30,000 high school students with 40 interests, and I've taken two variables to summarize. I'm summarizing the age of the students, their min, their max, and the four quartiles, and I've summarized the gender of the students into female and male and number of students in each. And at this point, you should stop the video and ask yourself what questions you have about the data, and then resume the video and to see how I've approached it. So you should pause the video now. And now, assuming you've paused it and thought about this, here are my thoughts on this data. The minimum age of high school students is a 3. That's certainly unrealistic. That's faulty data. The maximum age is a 107. That's probably faulty data as well. So what should we do with this faulty data? If we know who prepared the data, we could show them this and ask that the preparer correct these values. More likely we don't have access to that person, so we should possibly delete these observations, or we could overwrite them with the mean or the mode or something else, but certainly we should do something with them. We shouldn't leave them in at these values. For gender, hopefully you saw the same issue that I did, that there are 27,000 values of gender, but there are 30,000 students. So 3,000 students chose not to identify as either female or male. That's probably too many students to delete those observations or to give them a value of the mode, which would be female. Perhaps these 3,000 students are unique classification by themselves, and we should call them that. We should call them not otherwise identified or something like that, and treat this as having 3 genders and not 2. Here's a different problem. This is the age-old problem. Is a tomato a fruit or a vegetable? And while botanists have answered that question, we're going to take a data analysis approach and see if we can use some quantitative techniques to answer it. So I have 15 food items, and I've categorized each one in terms of sweetness from 1 to 10 and crunchiness from 1 to 10. For example, the carrot, I've given a sweetness of 10 and a sweetness of 7 and a crunchiness of 10, and we know that's a vegetable. I've done that for all of them, and including the tomato, which I've given a 6 sweetness and 4 crunchiness, although we don't know what class it belongs to. And now we're going to let the computer analyze this and answer the question, which food is closest? So we plot everything on a graph. This is sweetness on the x-axis and crunchiness on the y. I've arbitrarily colored the items which I think are vegetables, the items which I think are proteins, and the items which I think are fruits. And I've added tomato, which is almost right in the middle of the graph. And tomato is closest to orange and grape, which we know are fruits. So K nearest neighbor, just looking at the closest item geometrically, and closest being defined as Euclidean distance, says tomato is a fruit. Here is a slightly different algorithm. This is k-means, and in k-means we're assigning clusters without knowing what the response variable is. We're defining clusters in such a way as to minimize the total within cluster variation. Within cluster variation says whenever we have a cluster, we have a center point, which we'll call the centroid, and we can measure the distance from each of these points to that cluster. Again, that's Euclidean distance. This time we're squaring the distance and summing them. And for each cluster, we want a minimum sum of these within cluster variations. So this algorithm works iteratively. It arbitrarily starts with a first cluster, measures these total withinness variations, and then resets the clusters because it moves data points around and recalculates the clusters, and keeps doing this until there's no more possible changes in the clusters. So this final iteration got most of the vegetables right, although carrot is outside of it. Banana is outside the fruit items. Again, tomato would be closest to the fruits, although tomato is not inside this cluster. The student interest data set had 30,000 students with 36 interests. That's a big matrix. We arbitrarily chose 5 as the number of clusters. We could have chosen 3, we could have chosen 10. With the 5 clusters, the author of the text from which I took this problem named the clusters as princesses, brains, bad boys, and etc. You could have given it different names. Would this be useful to a marketer? Well, a marketer who's advertising sports equipment would probably want to advertise it to the people in cluster 4. Someone marketing something else might want to market it to cluster 1, and I think this would be useful to a marketer. Here's a different problem and a different technique. This is called association rules or market basket. Here we have a data set of store transactions. There are 5 transactions, so a transaction will provide us with the products that this customer has bought. So customer number 1 bought bread and milk. Customer number 3 bought milk, diapers, beer, and soda, and so on. So with this, we're interested in what rules can we create from this, such as people who buy bread are likely to buy milk. And we denote that as brackets around the bread, brackets around the milk, and an arrow. Although the first category could have more than one item in it. So continuing with this problem, if we only had one item in each set, we could simply do a correlation matrix and look for high correlations. But that limits us to 2 items. We also want to consider more than 2 items, so we can't use a correlation matrix for that. But what we can do is consider 3 measures: support, confidence, and lift. Support asks how many items are in both these sets and divide by the number of total items. Confidence asks what's the probability of buying Y given that you've bought X, and that's the number of items in X and Y divided by the number in X. And lift asks what is the probability of buying Y given that you've bought X but controlling for the popularity of Y, and that's the support of X and Y divided by the support of X times the support of Y. And here we're looking for lifts greater than 1 because that's a likely association. So there are lots of positive rules. We can pick 1 item out of the 6 ways. We can pick 2 out of the 6, 3 out of the 6, or all 6 out of the 6. That gives 57 possible rules. We don't want that many rules. So let's limit ourselves to a support of at least 60% rather, 60%. Then we can prune our search, because if a 1 item transaction is unlikely, then all supersets of that item are also unlikely. A superset is if A is a subset of B, then B is a superset of A. So B could have all the items as A plus others. So once we start eliminating some 1 item transaction sets, for example, we've eliminated eggs and soda because their support is less than 60%, then we can eliminate larger sets containing eggs. So all the supersets of eggs get eliminated. So we will eliminate some 2 item transactions, and in addition to ones containing eggs and soda, we'll eliminate these 2. and will eliminate lots of 3-item transactions and we'll eliminate these 3. And that leaves us with only 4 possible rules with a support of 6. And the interesting one is the diaper in the beer, which has a lift of 1.25. So this says people who bought diapers are likely to buy beer. And is this logical? And perhaps this occurs with new parents. The new parent goes to the store for diapers, and the new parent is stressed being a new parent, and maybe decides to buy beer. The groceries data set had 10,000 transactions and 169 items. That's a lot of potential rules. So it takes a pretty small support threshold if you're going to find any useful rules. Support of 60 is way too high. And this creates actionable, trivial, and inexplicable rules. The rice sugar people who buy milk, that's a trivial rule, probably not too helpful. People who buy plants buy milk, that's hard to explain, but that could be useful. Maybe the store manager should put the plants near the milk. And the herbs and the root vegetables, that's probably an actionable rule. And maybe people who buy herbs should be given coupons to buy root vegetables. The famous real-life example of something in the grocery data set is the teenager who was sent by a large department store coupons for diapers. And the story goes that the father of this teenager was just incensed at this and complained to the store manager. But it turned out the store had done a data analysis of its items and transactions and decided that certain characteristics of buyers, such as people who buy unscented lotion and other items, are likely to want to buy diapers. And sure enough, this teenager was pregnant and hadn't told her parent. So the data analysis worked, although it's possible the story is folklore. Now we're going to move to decision trees. Remember the game 20 Questions you probably played as a kid? That's an example that can be plotted as a decision tree. So for example, suppose I'm thinking of a mathematician who has a chapter in E.T. Bell's Meta Mathematics book. And suppose we limit our questions to yes or no and no compound questions. So what are some good questions and what's your goal with the first few questions? Well, if you think about it, you don't want your first question to be something like, is the answer Archimedes? Because if you're wrong, you've only eliminated one item from the much large data set of possible items. So what you want are some good first questions that will eliminate a lot of items at once. And the questions with your responses can be plotted as decision trees. So a decision tree is a tree-like graph. It's non-parametric. You don't need to know anything about the parameters or distributions of your data. It's easy to understand and visualize. The target variable is usually categorical. And the predictions are based on the best split of each input variable to get as homogeneous or pure branch as possible. And the computer does this by looking at all possible partitions and calculates the best possible splits at each branch. So here's a data set to answer the question, will it rain tomorrow? And there are 365 observations of 22 variables each, quantity of rainfall, air pressure, hours of sunshine, and so on, with the answer whether it rained tomorrow, yes or no. So this is the tree that the decision tree algorithm built from that data. It's a pretty small tree and only uses a few variables. The first split was the air pressure at 3 p.m., either greater than or equal to 1012. If the pressure was yes, greater than or equal, Then it goes down this path and asks about the clouds at 3 p.m. If the answer was no, it goes down this path and asks about the sunshine. And then it splits one more. And finally, there are 4 final nodes. So if you went down this path, you're a 95% chance that node will not rain. If you went down this path, it's a 67% chance, yes, it will rain. And that's how these algorithms work for decision trees. It's all done behind the scenes. Decision trees are used for prediction, also for assessing the importance of variables. So in that last tree, it only used a few variables and decided the others were irrelevant. It's used in medical diagnoses, desirable candidates for loans, college acceptance, financial decisions, and so on. And it's similar to regression. Here's a tree I've done on a baseball problem. The baseball problem is which is more important, pitching or hitting. I had 100+ years of data, and my first concern was how many years of data did I want to use? And I made a specific decision based on my domain knowledge of the sport of baseball. Someone else would likely make a decision of different number of years to use. And that person may have better or less domain knowledge than I have. But in any case, I made my decision. And having done that, I had lots of variables to play with. On base plus slugging is one of them. Pitching runs is another one, comparing my pitcher's team's runs to the rest of the league. This is a slightly more complicated tree than the last one, although it's too only used a small number of variables. And then depending on which path you went down, you have a pitching or hitting decision. And the decision of the tree was that pitching was more important than hitting, which is what a lot of baseball experts who are not data scientists would agree with. Here's the caravan problem, and caravan insurance problem. Should owners of caravans buy insurance? And my first question when I saw this is, what's a caravan? And I had to look that up to see what it was. A caravan is a trailer that you can use for housing, but it's a trailer that is towed to a motor vehicle. So a vehicle that has housing is not a caravan. There were 5,800 observations with 86 variables. This was an imbalanced problem because 94% of the observations were no. So if you just do nothing, you can be 94% accurate. I had outliers. I had missing data, not availables. A lot of my independent variables were correlated, so I didn't want to use them all and or skewed. I had politically incorrect predictor variables. I had religion. I really didn't want to make decisions based on a person's religion. And I ended up rebalancing the samples and creating some new variables. So finally, there's text analysis. And as an example, when Big Bill says to be or not to be, what I hear him saying is to be or not to be. So how do writers differ quantitatively is what text analysis is. So here are a few different measures of quantitative differences. One is characters per word, number of words per sentence. Probably Big Bill is much higher on these than I am. And actually these were things measured by mathematician / logician De Morgan of De Morgan's laws. He measured these when he analyzed Shakespeare's writings. Other ways to analyze are percent of unique words, percent of frequent words, use of sensory adjectives, adjectives that invoke seeing, touching, smelling, and so on. Use of sentiment words, words that have sentiments such as happiness, sadness, anger, and so on. Use of positive or negative words, verb-adjective ratio, and complexity, grade level readability. And by the way, the grade level readability comes in the Florida insurance laws, where by law, a Florida auto insurance policy has to have a certain grade level readability. And so text analysis is done to make sure these Florida insurance policies pass that portion of the law. Here are some uses of text analysis. Did Shakespeare really write all the works that are attributed to him? Did Hamilton really write all 51 Federalist Papers? And the play Hamilton has one answer to that. Mathematicians have a different answer. Which Beatles songs did John write, or which ones did Paul write? Which tweets did Trump write, or did his staff write? Compare the sentiments of characters, compare books, presidents or judges, compare consumer products, politicians, or course valuations, and perhaps more seriously, can we use text analysis to predict spam, crime, fraud, or terrorism? And there are people in the government certainly concerned with the crime, fraud, or terrorism, and they're using text analysis on people's texts to try and predict these three crimes. Here are some notes on the textbooks I've used to come up with some of these problems. There are a lot of good texts out there. There are a lot of good websites. There are lots of YouTube videos. Generally, people who do data analysis use the computer language R or the computer language Python. These are much more efficient than using Excel. And finally, thanks for listening. Now I invite your questions, and here's an email site where you can find me. And thank you very much.